All right, let's dive right into this explainer. Today, we're going to completely demystify the programming pipeline. We're taking a really fascinating journey, transforming raw, abstract human logic into flawless, executable machine instructions using the C programming language. Let's get into it. To really ground our journey today, we're going to use a super relatable real-world case study throughout this explainer. Think about it. How do we actually evaluate academic performance using a machine? Specifically, how do we systematically take raw student marks, crunch those numbers, and spit out an accurate percentage? It sounds pretty simple on the surface, but the logical process behind it, it's a literal masterclass in structured thinking. Here is our roadmap for getting there. 1. The core problem-solving approach. 2. Algorithms and flowcharts. 3. Building blocks of C. 4. Operators and expressions. And 5. Developing the C program. This brilliantly illustrates our think, plan, build framework, giving us a highly structured path from fundamental problem-solving all the way to a validated C program. Section 1. Core problem-solving approach. Let's start right at the foundation with the thinking phase of our framework. Okay, so before we even think about typing a single line of code, we need some clear end goals, right? We have to understand the fundamental problem-solving approach by recalling the basics of algorithms, flowcharts, and C. This isn't just about memorizing syntax. It's about learning how to apply logic and even how to investigate a control system's components, often collaboratively as a team, to set ourselves up for success before the keyboard is even touched. Section 2. Algorithms and flowcharts. Now, what's really interesting about this next step is how we transition from abstract thinking to visual planning. So, what are our blueprints? Well, an algorithm is basically your logical problem-solving approach. It's the raw, step-by-step logic needed to solve an issue. A flowchart, on the other hand, takes that exact algorithm and uses standardized symbols to visually represent it. Think of the algorithm as your written script and the flowchart as the visual storyboard. These blueprints let us lock down our logic way before we start worrying about the specific rules of C. Let's actually apply this to our case study. Task 1. We need to write an algorithm and draw a flowchart specifically designed to calculate the total marks, percentage, and grade of a student. Notice we still aren't coding yet. We are strictly mapping out our strategy to make absolutely sure our logic is sound. And here is exactly how that strategy breaks down step by step. Step 1. Input the raw marks. Step 2. Calculate the total marks. Step 3. Calculate the percentage based on that total. And finally, Step 4, determine the final grade. By successfully applying algorithmic thinking and mapping this out, it keeps things clean, logical, and perfectly sets us up for the next step. Section 3. Building blocks of C. With our blueprint firmly in hand, let's move into the building phase and examine our materials. To keep things from getting overwhelming, it really helps to organize these foundational C elements into neat little buckets. It's basically like learning the grammar of a new language. The character set contains the basic letters, digits, and symbols the compiler recognizes. Identifiers are the custom names you make up for your data, while keywords are reserved words C kind of claims for itself. Data types classify our data so the computer knows if it's looking at, say, numbers or text. And finally, constants are fixed, unchanging values, whereas variables are the specific memory locations holding data that can change over time. But wait, before the main program actually runs, there's some backstage setup required. C relies heavily on the preprocessor and library functions. Think of the preprocessor as the prep cook, getting the kitchen ready before compilation. Library functions, meanwhile, give us access to prepackaged capabilities, like a recipe book, so we don't have to reinvent the wheel every single time we want to print text to a screen or do a standard math operation. Section 4. Operators and expressions. We have our individual blocks, but now we need the mortar to hold them together. C gives us a massive toolkit of operators to manipulate our data. Under core math and logic, you've got your standard arithmetic, relational, and logical operators. For value manipulation, you'll be using assignment, unary, and conditional operators, and for the real heavy lifting behind the scenes, there are advanced operations like bitwise. Think of these operators as the verbs of our programming language. They tell the computer exactly what actions to perform on those data blocks we just talked about. So, when we combine our variables and constants with these operators, that's when the magic happens. We create expressions and statements. These are combinations that evaluate to a single value and directly instruct the program to take a specific action. This right here is the actual heartbeat of your program, where the real computational work gets done. Section 5. Developing the C program.
It's time to finally put it all together into a functioning structure.
It's honestly incredibly satisfying to see how the visual logic from our Task 1 flowchart maps so perfectly onto the actual structural syntax of a C program. What started as just an abstract human thought became a visual storyboard, and now it literally transforms into executable, machine-readable code.
Every single C program basically follows this super elegant, predictable flow. First, data input, bringing raw information into the system. Second, processing, using those expressions to crunch data and apply our logic. And third, data output, delivering the calculated result right back to the user. Input, process, output. It's a highly efficient cycle.
Which brings us to the real climax of this explainer, executing our original goal using the C language. Task 2. We are going to write a program that inputs the raw marks of 5 distinct subjects and calculates the final percentage.
By completing this, we successfully apply fundamental C programming constructs to validate our academic performance setup. We input the marks of the 5 subjects, the program relies on our structured expressions to calculate the total marks. And then, it mathematically determines the exact final percentage. The machine does all the heavy lifting, but it's doing exactly what our human logic rigidly instructed it to do.
And you know, that is the true power of programming right there. The pipeline from abstract problem solving to visual flowcharts, all the way to executing a functional C program, it's no longer a mystery. We've built the bridge. So now that you fundamentally understand this connection between human logic and machine execution, how are you going to apply algorithmic thinking to your next big challenge? The tools are entirely in your hands. What are you going to build next?